Last time I started with convergence analysis and how to show that either a one-step method or a multi-step method is consistent in determining order of accuracy. And we also looked at stability for a one-step method. So I'm just going to continue completing that. But it's definitely stability for a multi-step method. So here we have a general multi-step method that covers either atoms or BDF or other methods that don't fall in either category. And the way that we show that this is stable is by checking for what's called zero stability. And the name zero stable, the term zero stable is suggested by considering literally the simplest ODE of all. Y prime is equal to 0. In that case, y of t is just equal to a constant, and that constant is y naught. So what happens when you apply your multi-step method to this problem? So your function, normally your ODE is y prime equals f of ty, so f is 0 everywhere. So the right-hand side of a multi-step method, that part is just going to be 0. So now all you have is your y value satisfying this equation. And this is called the recurrence relation. It's an n+1 term recurrence relation because the number of terms that you have in the summation is n+1. So now the thing is, here we only care about the solution being bounded. We do not care about accuracy. That's what consistency is for. So our goal here is to find conditions on these alphas so that the y values that are produced at least do not grow with time. So this gets into the theory of recurrence relations, which is something that's good to know about anyway for a variety of problems. What do you do with the characteristic equation? And I would love to take the time to fully derive why this approach works. It is something that I do in Cal 3, for example, with Fibonacci numbers, so two of you have seen that already. What do you do? The idea is you form what's called the characteristic equation of a recurrence relation. And the way they always teach about this is they will assume that your solution of your recurrence relation is a power of some number. Like it's like yn equals z to the n for some number z. We never explained where that assumption comes from, but it comes from what's called a generating function for these for your solution. So it is something that can be shown rigorously. But by making the assumption that yn equals some number raised to the n power, so like lambda to the n, you get what's called the characteristic equation of a recurrence relation. And all that is you replace yn with lambda to the n, and what you get is your lambda is satisfied this polynomial equation. So then you find, and then the coefficients alphas, those are given because those define your recurrence relation. So then once you have the roots of your characteristic equation, then your solution of your recurrence relation, your yn, can be shown to have this form, that it's a linear combination of the roots raised to the nth power to get yn. You have some coefficients. The coefficients come from the initial conditions of your recurrence relation. So for multi-step method, that means your initial data and starting numbers. And then, if you have repeated roots, you may also have powers of n. So for example, if you have a root of multiplicity 2, then you have like lambda to the n, and then n lambda to the n. So the powers of n start from 0 up to whatever the multiplicity of a root is, -1. So if all the roots are simple roots, multiplicity equal 1, you don't have any factors of n. So then if you know what your solution of your recurrence relation, therefore the computed solution from your multi-step method, has this form, you want to make sure that this function of n cannot grow with n. And that leads to what is called a root condition. This is how we determine zero fidelity. So, first of all, to ensure that this does not grow with time, that all the roots have to be less than or equal to 1 in absolute value. Because certainly if you have a root larger than 1 absolute value, this thing's definitely going to grow. Also, we don't want these powers of n in here in the case where the absolute value of the root is equal to 1. So that's the second part of the root condition. If the root has absolute value 1, it has to be a simple root. It cannot be repeated. So if these conditions are satisfied by the roots of your characteristic equation, then we say that your multi-step method is zero stable. Now, I don't show it here, but it can be shown that if your multi-step method satisfies the root condition, then it also satisfies it is stable in the sense of the way that it defines stability last class, where a change in initial data leads to a bounded change in the solutions for all n. So fortunately, for multi-step methods, making sure we're stable in that sense is very easy to check. Also, it's determined entirely by your alphas. So the betas for the multi-step method play no role in this determination, which is interesting. Okay. There are two other sub-notions of stability. So a method could be strongly zero stable or weakly zero stable. So if you look at all the roots that have absolute value equal to 1, so lambda equals 1 is always going to be a root just to ensure consistency. If there are no other roots that sit on the unit circle, like absolute, in other words, of absolute value 1, then we say it's strongly zero stable. Otherwise, it is weakly zero stable. For example, suppose a multi-step method has plus and minus 1 as roots. As long as they're simple roots, the method is zero stable. But having minus 1 as a root might not be a great thing, because because then your solution has a factor of minus 1 to the n in it, so it has like an oscillatory component, and you probably don't want that. Still stable though. It's like, yeah. All right, so questions about the root condition. It's one example about root condition. So Adams methods they all have the same alpha. It's always y plus 1 equals yn plus other stuff. So if you have an m-step Adams method, this is a characteristic equation. Lambda m minus lambda n minus 1 equals 0. So that is very easy to obtain the roots from. So you always get 1 as a simple root, and then all other roots are 0, and those are repeated. So not only do all of the Adams methods satisfy the root condition and therefore stable, they also satisfy they're strongly zero stable. Here's another example. So this is a multi-step method that is neither an Adams method nor a BDF. It's called Simpson's method. The name comes from the choice of betas here. Notice we have we use values of time tn plus 1, tn, and tn minus 1. And the middle time of those gets 4 times as much weight as the ones before and after it, which is similar to how Simpson's rule behaves for numerical integration. So this is an unusual method in that it is only a two-step method, so it only goes back to time tn minus 1, but it is fourth order accurate, so it's surprisingly high order of accuracy considering how little information it uses. Whereas the Adams-Bashforth method would have to go all the way back to time tn minus 3 to be fourth order accurate. Whoops. Okay, but so in this case we have y plus 1 and yn minus 1. So your characteristic equation turns out to be lambda squared minus 1 equals 0. So that has the roots plus and minus 1. So that is a weakly stable method, which is probably why you don't hear about very much. Also, it can be shown that if you have a BDF, M-step BDF, and M is greater than 6, then it does not meet the condition for 0 stability. So all BDFs with order greater than 6 are 0 unstable. Maybe you see the proof of that. Like, one thing to choose any example, like say a 10-step BDF, you compute the roots, you see like, oh, okay, it's not stable, and you try for however many examples you'd like to prove that you're going to get a root outside the unit circle for all n greater than 6. Usually not an easy thing to prove. Okay. Oh, okay. So I mentioned here about most of them is 0 stable, then it fulfills the definition of stability that it gave last class. And I want to mention this text, Isaacson and Keller, this old text from the 60s. It really tells the whole story in terms of like, for example, proving that if most of the method satisfies the root condition, it is stable in that sense. That 0 stability does imply general stability. So this is a great book for like filling in the blanks. It also shows that for both one-step and multi-step methods, proving that consistency and stability in the sense that I defined them last time really does give convergence. So I guess that's their counterpart to the lax equivalence here. Speaking of, okay, so now that it covers stability for both one-step and multi-step methods, we can look at convergence. That's what we really care about. Okay, so and so there's something actually. Did I prove it here? Oh. Okay, yeah. So I'm going to show you here that in the one-step case, that if it's consistent and stable, that it is convergent. There's a theorem called the Dahlquist equivalence theorem. Dahlquist proved a lot of useful theorems regarding multi-step methods. So it's a slightly different statement. If you have a consistent multi-step method, then it is convergent if and only if it is 0 stable. So we have a partial converse in that case. Now, okay, I want to tweak my notation here. I should have looked at this before class. I have my 5 function depend on yn, but not yn plus 1, because we don't really need that. I'm going to have to edit this as I go. Sorry about that. Okay. So to prove that a consistent, stable one-step method is convergent. It's stable if your one-step method that's defined by a function phi is Lipschitz continuous in the yn argument. So it is. So this is how you can show that it's stable. need to recover this from last time's notes, because things changed a little bit. Okay. Okay. So this expression should be changed. It's just 1 plus HL by. Okay. Make sure that matches up. Okay. Yeah, here I have just L. Last time's notes, but I'm calling it L sub phi over here. Okay. I don't have this condition anymore. Okay. Now, the approach I take to show convergence from here is that it's similar to how I prove convergence for a specific case of Euler's method. So I define at any time Tn, the approximate solution minus the exact solution, the En, that's the global error. So that's what I want to show goes to 0 as H goes to 0. Now, so the idea is I substitute the exact solution into my one-step method, and I have this where tau n is the local truncation error. And keep in mind that because we're assuming the method is consistent, that local truncation error goes to 0 as H goes to 0. So then, okay. So then what I do here is, if I take this and subtract it from the from a numerical method, then this is what I get. I get this relationship between the new error and the previous error. I think that is a little bit. Okay. Sorry, I think I need to fill in some more steps here just to make sure that everything turns out the way it should be. Okay. Yeah. Because the computer solution satisfies the numerical scheme, of course. Okay. So by subtracting this equation from this one and applying the fact of the Lipschitz continuity, so this minus this gives me En plus 1. This minus this gives me En times 1. And then this minus this gives me H times the Lipschitz constant times the difference in the y arguments, yn and ytn, but that's En again. And then I also have this local truncation error turned over here, so I just need to get rid of this 1 over delta that shouldn't be here. Okay, so now I have this relationship between new error and previous error. And then we have this local truncation error term as So then, what I have is, instead of jumping to this conclusion, I'm just gonna run with this and actually work out steps for you, so I can make sure everything's right. Alright, so from applying this repeatedly, what I get is En plus or equal to 1 plus HL phi N E naught, but E naught is 0, that's the error in initial data. Plus, and then I have a sum, N minus 1 plus HL phi I times this part, this term right here, coming from the local truncation error. Actually, what I'll do in this case is I'll take the maximum. Sorry, I'm in trouble typing. All right, so then we have the maximum of this term over all time steps, because we're just one upper bound anyway, times all these factors accumulate. We hit, and if you're not seeing where this comes from, this is following the same steps that I showed in more detail when working with Euler's method. Because every time if I write En in terms of En minus 1 using this recursion relation, En minus 1 to En minus 2, you get powers of this factor times this multiplication error term every time you expand. So that happened with proof the convergence for Euler's method. So now I have this, but here this is a partial sum of a geometric series, and so we use a formula for that. Now let's refresh your memories what it is. So we have 1 plus r squared, so on up to our n minus 1 equals 1 minus r to the n, or 1 minus r. Okay, so now I'm going to use that. Oops, I put this in the wrong place. Okay, so now I use this formula to put this summation okay, now I have this bound. Okay, this part is 0 because E0 is 0. And then this summation becomes, okay, so we have 1 minus 1 plus HL phi the n. Actually, I'm going to negate both terms just for convenience for later. I'm going to have 1 plus HL phi minus 1. But we'll want to cancel down below. Also, we have 1 plus HL phi and that is less than E, the exponential of HL phi. because this part is just the first two terms of the Taylor expansion of the exponential. And HL5 is positive, so we know that this is a strict lower bound. Okay. All right. So now I'll simplify this denominator. Okay, we have this factor of h canceling with this one. Okay. And then here I replace with my exponential. So that's e to the HL phi. Okay. But then all of that's raised to the nth power. And n times h is equal to the difference in is equal to the difference between the final time and the initial time. So by incorporating this n into the exponent, then I have, I just need to edit this, but I don't need to have a factor of 2. I don't have to be divided by delta. But otherwise it's, so then I have this, that this is my bound on the global error. And this constant here is independent of h. So now we can use the fact that as h goes to 0, this is fixed constant. This part is going to 0 because the method is assumed to be consistent. Therefore, the global error goes to 0 as n goes to infinity. Okay, I realized I was a bit slipshod because I was editing a proof that needs to be edited. At least there's a chance to fill in some details. Actually, I want to clean up some notation here. This should be tau I at h. I'm taking the maximum of all local propagation errors over all steps, I going from 0 to n. I'll fix that down here too, and throughout. Yeah. Okay. So to recap, now that all this is cleaned up. Okay. So this is summarizes the flow here. We're assuming the method is stable. That gives us its Lipschitz. And here we have, for consistency, we have, by substituting the exact solution into the method, one-step method, we have our local propagation error term here. Subtract from this, from the method itself, and we get this. And then, and this comes from applying the Lipschitz condition that we have for phi. Then we apply this relation repeatedly. So instead of having a relationship between en plus 1 and en, we have a relationship between en and the initial error, which is 0. So we're just using initial data here. And then applying it repeatedly yields to this summation, which we can bound because it's the partial sum of geometric series, so we use this formula here. And that simplifies things to this. Then we bound this by an exponential. That allows us to make use of the law of exponents, and we can incorporate this n into the exponent. N times h is equal to the difference between Tn and T naught. So now we have the exponential of L phi times Tn minus T naught. But that can be bounded by exponential of L phi times the final time minus the initial time. So now we can say that the global error is bounded above by the maximum local truncation error times a constant. The expression in large parentheses is independent of h and n. It's just a fixed constant. And then by using the assumption of consistency that the local truncation error goes to 0 as h goes to 0, the global error goes to 0 as h goes to 0 across all time steps. So actually this statement is true for all n for which we have a time step. N to T minus T naught over H. Okay. And of course, H is going to 0, so ultimately we'll have in the limit we'll have infinite time steps, but the errors for all these time steps all satisfy this. And so the process of proving this is largely the same as it was for Euler's method. Really, the only difference is that, like in Euler's method, we have ellipsis condition applied to f. For general one-step method, we have ellipsis condition applied to phi, but the final one-step method. And then for Euler's method, we have this local error term that's hy double prime over 2. For general one-step method, we use whatever expression there is for its local truncation error. Now, for both one-step and multi-step methods, the order of accuracy for the rate at which the global error goes to 0 is the same as that of the local error. That's actually why the local truncation error is defined by, you substitute the exact solution in the numerical method, and then you divide by h. So I didn't really make clear before why I did that, but this is why. So that if you show that the local error is second order, for instance, and the global error is second order. So just to have that consistency between the two. It'd be a pain to say, like, oh, you subtract one, let's make them same. Okay, questions about showing convergence? So we don't really have to show convergence anymore. You just show consistent and stable, and then you know it's convergent. So prove it once and you forget about it. Okay. Now, things get challenging when it comes to stability and such. If you go for convergence, when you have an ODE that is stiff. Now, if you look at different books, you might find different definitions of what it means for an ODE to be stiff. Some might only apply the concept of stiffness to a system of ODEs, rather than a single one. The definition we're using here is that an ODE is stiff as its exact solution has terms with the k to 0 as t goes to infinity, but also have very large derivatives. So, like, let's suppose your exact solution has a term of the form e to the minus ct, where c is a large constant. So, or assuming c is positive. So that's an exponentially decaying term. As t gets larger, that term is making hardly any contribution at all to the solution. But the k derivative, you take that exponential, you multiply by minus c raised to the k power. Now, in general, if you have a time-stepping method that's accurate to order P, it involves a P plus first derivative in its error formula. So that term in a solution may be small, but it might make a large contribution to the error. And the higher order the method is, the bigger this problem becomes. So you end up having, if you increase the order of accuracy, there's sort of a diminishing returns effect here. That you're not gaining as much because that other portion of your error. I mean, we pay so much attention to the power of h, the exponent of h, in the error formula because that determines the order of accuracy. But it's not the only thing that's there. If that derivative portion is large, then you're not really getting as much accuracy as you think. Now, stiffness is a property of the problem, of the underlying ODE itself, not the choice of method you use to solve it. If you have a stiff ODE, it's going to pose difficulties for whatever method you use. It's like solving A equals B. If the matrix is still conditioned, that is a property of the problem with itself, not your choice of Gaussian elimination or iterative method. Ill-conditioned matrices are pose difficulties for all kinds of system solving methods. So sometimes you just get a bad problem. So because of this, if you want to have a solution that has correct qualitative behavior and be reasonably accurate, you're going to need to use time step h that is far smaller than the spacing that you would need to accurately represent the solution. Because suppose the solution is very smooth, then and your time step method is basically sampling a solution that points to a certain spacing. If the solution is very smooth, then just to represent the solution accurately, your time step h does not need to be very small. But if the problem is stiff, it needs to be small anyway, just to compute your solution at all. So you end up incurring a lot of extra computational effort. So this is why we want to try to recognize when a problem is stiff and try to find better ways to solve such problems. So here's an example. Y prime equals minus 100y. And the initial value is 1. So this is the exact solution, e to the minus 100t. So as t increases, it goes to 0 very rapidly. But now, let's apply Euler's method to this problem. So you're substituting your time derivative being minus 100y. So then y plus 1 is equal to yn times this factor right here. So if I choose h equal 0.1, normally that seems like a reasonable choice, then your solution is going to grow exponentially. It's also going to oscillate. Because it's going to be minus 9 to the n, but the solution is supposed to go to 0. If I choose a smaller h, like 10 to the minus 3, then at least we have exponential decay, 0.9 to the n. It's not decreasing at the right rate, but at least the solution has the correct qualitative behavior again. But that's the point. You have to choose a much smaller h than you'd like to, just to get a reasonable solution at all. So to determine what a suitable h should be, and what kind of h is needed to get the correct qualitative behavior, like the solution that's supposed to decay, we use this equation called the test equation. The y prime is equal to a constant lambda times y, and we assume that the real part is negative. A real part of lambda is negative. That way, okay, so here's the exact solution to e to the lambda t. And if the real part of lambda is negative, then this is going to exponentially decay over time. But if the real part is large in absolute value, so it's very negative, then this is a stiff ODE. So for one-step methods, when you apply to a test equation, you get something like this. You get y plus 1 equals yn times some function of your time step h times the parameter lambda. Now, what kind of function is this? It's a polynomial if the method is explicit, like Euler's method, or if it's an implicit method, then this is a rational function of h lambda. Either way, it's supposed to be an approximation of e to the h lambda, which is what you multiply by to produce the exact solution. So we need exponential decay. So this, whatever you're multiplying by, it needs to have absolute value strictly less than 1. So for example, a modified Euler method, also known as the explicit trapezoidal method. So here's the method itself. And then I apply that to the test equation, and I end up having y plus 1 is equal to yn times this factor to large parentheses. So I need to ensure that this factor is less than 1 in absolute value. Now, that's equivalent to determining for what x is this function of x strictly between 0 and 2. And through some algebra here that I won't get into, we end up having h lambda in absolute value has to be strictly between 0 and 2. So the larger lambda is, the more stiff the problem is, the smaller h must be to ensure a solution that with the correct behavior that is decaying when the exact solution is also supposed to decay. So this is the kind of thing we get for a one-step method. We need this condition to be satisfied. What about multi-step methods? Again, you apply your method to the test equation, and we end up with this recurrence relation, which is a different recurrence relation than last time when I was covering zero stability, because with zero stability is determined entirely by the alphas in your multi-step method. But now for determining the correct solution to the test equation, the betas come into play also. So now, the characteristic equation for this recurrence relation leads to this polynomial as a modification of the one for zero stability, and that's called the stability polynomial. Now, so now, instead of the root condition for zero stability, what it requires that the roots of this stability polynomial must be strictly less than 1 in absolute value. So with zero stability, you could have a root that's on a unit circle, no more. So for example, suppose we have a 3-step Adams-Bashforth method. So this is the method. So then the stability polynomial, by filling in the alphas and betas from up here, we get this, which is a rather nasty polynomial. It's not something we could like try to find the roots of on paper or anything. But I'm going to go ahead and let lambda equal to minus 100. So if I choose so not particularly small step size, h equals 0.1, and the largest root is way out of bounds. So the Adams-Bashforth method would be unstable for this problem. It would produce an exponentially growing solution. As long as if I choose a much smaller h, so 0.005, then we do get all roots less than 1 magnitude. So unfortunately, like to determine where the method is stable is really done like numerically. You try a whole bunch of lambda values in the complex plane. For each lambda value, you form its polynomial, you compute the roots, and you determine the absolute value of the largest root. And if that is less than 1, then it's stable, otherwise not. Yes?
So it's a trial and error process?
Yeah, no. But that leads to what's called the region of absolute stability. Yeah. And trial and error is, that is what we did actually. Yeah. But trial and error sounds random, but usually it's like very ordered. So, the region of absolute stability, and this applies to either one-step or multi-step methods, is a region within the complex plane such that h lambda is a suitable value in terms of ensuring qualitatively correct behavior of a solution. So for one-step method, it means that absolute value of q of h lambda is less than 1. Or for a multi-step method, that this stability polynomial Q of U with parameter H lambda, so Q my B's are different. I probably should use a different letter, but oh well. Has roots that are less than 1 magnitude for multi-step case. So you apply the appropriate criteria, and so for whatever value of H lambda you get stability, that's the region of absolute stability. What we really like to have is if your region of absolute stability includes the entire left half of the complex plane, where if a real part is negative, then we say that the method is astable. So a lot of important ODEs are covered by that left half plane. So for example, backward Euler. If I apply backward Euler to the test equation, then I have yn plus 1 is equal to yn times this factor right here. Now, if a real part of lambda is negative, then this denominator is going to have a real part that is strictly greater than 1. So what that means is this factor in parentheses is going to be less than 1 in absolute value always. So backward Euler is astable. The implicit trapezoidal method, that is a second order method, is also astable. Now this leads to some more theorems from Dahlquist. Dahlquist's barrier theorems. So the first barrier theorem says that if you have a zero stable multi-step method, the order of accuracy is that most n plus 1 if n is odd, and n plus 2 if n is even. So for example, actually one of the examples I gave earlier illustrates the upper limit of this. Simpson's method is a 2-step method, so m equals 2. It is a zero stable method, it's just weakly zero stable. The theorem does not distinguish. So it has the maximum order of accuracy possible for a zero stable multi-step method, that is 4. So you can have quite high order accurate methods for a low number of steps, but then they're not going to be zero stable. The second Dahlquist barrier theorem says that there is no explicit method that is astable. So the two examples I gave you, backward Euler and the trapezoidal method, those are both implicit methods. Also, it's not possible that an astable method of order greater than 2. Yeah, so the example we gave, backward Euler is first order accurate, trapezoidal method is second order accurate, the highest order accuracy you can get for an astable method, what's this here? Also, there are other second order methods that are astable, but the one with the smallest asymptotic error constant, so let's multiply the h squared, is the implicit trapezoidal method. Because your error formula would have, for the trapezoidal method, it'd have like a y triple prime at the unknown point times h squared times some scaling constant. So that scaling constant is smallest for trapezoidal than for other second order accurate astable methods. Okay. So kind of a bleak picture as far as zero stability goes, but or astability rather. Oh well. Okay, so that's convergence analysis. And let's see. Actually, that concludes time stepping. That includes discussion for initial value problems. So the last material to cover is chapter 13. It's boundary value problems for ODEs. So I'll cover that for the next 4 class periods. Okay, do we have any questions about it?
I have questions, but they're not this class
Alright, I guess that'll do it.